first question, which basically says that which of the following set with a given addition and scalar multiplication operation do not form a vector space. Okay, so before looking at the given vector sets in this question, first let us see some important axioms that are required for a vector space. So in case of addition, there are mainly four important axioms. The first one is if there are two vectors that belong to one particular vector space, then the sum of those vectors should also belong to that particular vector space. The second axiom is associativity of addition, which basically states that the way we group the vector while adding doesn't matter, the result is going to be the same. The third axiom is the existence of zero vector, which state that there exists a zero vector in every vector space, where if we add that zero vector with any vector in the space, let us say v1, then the result is always going to that vector v1. The fourth and the last axiom is basically the existence of additive inverse, which basically states that for every vector in a given vector space, there exists an inverse of that vector, such that if we add that vector with its inverse, we will get a zero vector. So, if we now look at the important axiom in case of multiplication, then there are mainly three important axioms. The first axiom is distributivity over scalar multiplication, which states that when adding scalar first and then multiplying it with a vector, it gives the same result as multiplying each scalar separately and then adding the resulting vector. The second axiom is the identity element of scalar multiplication, which states that multiplying a vector by 1, leave it unchanged just like multiplying a number by 1. The third and last axiom states that if we have a vector v, 1 belongs to a given vector space, then multiplying that vector with any real number, and the result will also belong to the same vector space. Okay, so now let us look at the given vector sets. The first set is basically v1 is equal to x comma y, such that x and y belong to a real number, and the addition is given as x1 plus x2 comma 1, and the scalar multiplication is given as cx comma 1. The problem in this vector set is basically that here a zero vector can exist, means that if we try to add any one vector from this vector space with a zero vector, then according to axiom the result should be same as the chosen vector, but here the resulting vector will be changed as the y term will be always equal to 1 in case of addition. Hence it will not form a vector space. Now we look at the second vector set, where it is given v2 is equal to x comma y, such that x and y belongs to real number, and the addition given as x1 plus x2, y1 plus y2, and the scalar multiplication is given as cx comma 0. In this vector set, the identity of the given vector will not hold, means that if we multiply any vector chosen from this vector set with 1, then as per axiom, it should be equal to chosen vector, but here the y term will differ as it will become 0. Hence it is also not going to form any vector space. Now if we look at the third vector set, which basically says that v3 is equal to x comma y, such that x and y belongs to real number, and the addition is given as x1 plus x2 plus y1 plus y2 comma x1 plus x2 plus y1 plus y1, and the scalar multiplication is given as cx comma xy. Now in this case, it will pass all the axioms for multiplication, but in addition, it will fail the axiom, which states the existence of zero vectors. Hence v3 will not form a vector space. Now if we look at the fourth vector set, which basically says that v4 is equal to x comma y comma z, such that x, y, and z belongs to real number, and x plus y should be equal to z, where the addition is given as x1 plus x2 comma y1 plus y2 comma z1 plus z2, and the scalar multiplication is given as cx comma psi comma cz. Since by barely looking at v4 vector set, we can clearly say that whether it is addition or scalar multiplication, it is in its standard form, hence it will pass all the axiom that are required for a vector space. So v4 is going to form a vector space. Now, let us move to the second question. The second question says that a healthy juice consists of 30 units of protein, 11 unit of carbohydrate, 53 unit of fat, and 213 unit of calcium. A juice maker make two type of juice type A, and type B. Type A consists of banana milk and almonds, whereas the type B consists of apple milk and almonds. In the given table, the amount of protein, carbohydrate, fat, and calcium present in each banana, apple, and almond in 100 milliliters of milk are given use the above information to choose the correct options. So type A consists of banana milk and almonds, whereas the type B consists of apple milk and almonds. Now, let us try to find the correct options. So first, basically, we have to check whether we can form a juice with right quantity for the given types, and whether it will be unique or not. So first, let's see for type A. The equation for the protein in type A is given as 2x1 plus 4x2 plus 6x3 equals 30. The equation for carbohydrate is basically 3x1 plus x2 plus x3 is equal to 11. The equation for the fat is basically x1 plus 3 e times 2 plus 15 e times 3 is equal to 53, and the equation for the calcium is basically 5x1 plus 100x2 plus x3 is equal to 213. Okay, so first let's see from where these equations came from. So type A consists of banana, milk, and almonds, and if we look at the amount of protein that each of these ingredients have from the given table, then we can see that banana have 2 units of protein, milk have 4, and almonds have 6 units. Similarly, we can do it for carbohydrate, fats, and calcium also. So now let's make an amalgamated matrix from this equation, and the amalgamated matrix is something look like this. And if we reduce this amalgamated matrix, then what we get is basically this matrix. And if we look at the third row of this matrix, then we can find that x3 is equal to 3, and from second row, we can make our equation of x2 plus 1.6x3 equals 6.8. And if we put the value of x3 that we just found from row 3, then we can find the value of x2, which is basically 2. Now from the first row of this matrix, we can make another equation, which is basically x1 plus 2x2 plus 3x3 is equal to 15. And if we put the value of x2 and x3 in this equation, then we can find the value of x1 is equal to 2. So we get the value of x1 equals 2x2 is equal to 2, and x3 is equal to 3, means that forming a healthy juice from the type A is possible, and the amount of ingredient required is also unique, so the option is going to be correct. Now similarly, if we look into type B and make again another amalgamated matrix for the type B, as we just made for the type A, and reduce it using some row reduction methods, then at the end we will get a reduced matrix something like this. And here from the row 2 to we can see that x2 plus 1.57x3 equals 7. It came from the row 2, and from the row 3 we can see that x2 plus 9x3 is equal to 53. Now if we add this to equation, then what we get is basically 10.57x3 is equal to 60, means that x3 if going to be a decimal number, but x3 is the number of almonds, and it should be a whole number, but here it is not. So from this point we can understand that type B is not possible, hence the correct option for this question is basically the first option and the last option, which is the first option is basically healthy juice can be prepared with the right quantity of ingredient of type A, and those quantities are unique, and the healthy juice cannot be prepared with the right quantity of ingredient of type. Let us now look at the third question. The third question basically says that consider the set of vector S from our 3, and we have to choose the set of correct options. The first option say that the singleton set of -1, 1, 5 is linearly dependent, but we know that set of vector are said to be dependent only when its linear combination is equal to 0, where all the C should not be equal to 0, but since it is a single vector set, and it is not a 0 vectors, so only value for C for which this given set will be equal to 0 is basically C is equal to 0, but as per the law, all C should not be equal to 0, hence this set is going to be linearly independent, means that the first option is wrong. Let's look at the second option. The second option say is that if alpha and beta belongs to S and alpha and beta are distinct, then a set of vector which contain alpha and beta only is the linearly independent set of vectors. So if a set contain 2 vector and are 3, then it is dependent only when both are scalar multiple of each other, but herein, as there are no such to vector present which are scalar multiple of each other. Hence we can say that this particular set is actually independent. Now in third option, we are basically asking that whether this given set of 3 vectors are dependent or not. To check whether this set of vector is dependent or not, we are going to check its determinant. If the determinant is going to be 0, then it is going to be dependent. But if the determinant is not 0, then it is independent. So if we look at V3, then we can find that V3 is scalar multiple of V1. As if we multiply the V1 with 2, then the result is going to be V3, hence its determinant will be going to 0, as we know that if any two row or column are proportional to each other, then their determinant is going to be 0, hence this given set of vectors is going to be dependent. The fourth option says that the set S is linearly independent set of vector. We know a fact that if a set of vector contain more vector than its dimension, then it is always going to be a dependent set. And here the vector space is of third dimension, but the number of vector it have is basically 5. So it is always going to be dependent. Now, similarly, explanation of all the other options are written below. You can pause and see the explanation. Until then, let us move further. So the fourth question basically says that we have a set of 3 vectors in our 3, and there's an unknown in the last vector which we have to find, and it is given that this set of vector is dependent. We know that if set of 3 vector form a square matrix, and if it is dependent, then its determinant will be always going to be 0. So let's make a matrix from this given set of vector and expand along the first row. After expanding it along the first row, equate the resulting equation with 0 and find the value of C just like this. So after doing all these calculations, the value of C obtained is minus 7/5. Let's move forward and see the fifth question, which say that there is a set of 3 vector S in our 3 with usual addition and scalar multiplication. If S is linearly independent, then what value of C cannot be equal to? So in this question, we basically have to find a value of C for which the vector is going to be dependent again. We will do the same method as we did in the last question. We will again find the determinant and equate it to 0, and the resulting value of C will be the answer of this question. So here is the matrix created by the given vector, and we do little row reduction here, and then expand along R2, and the value of C for which it will become dependent is minus 2. Hence the value of C cannot be minus 2. Now let us move to the sixth question, and it is a comprehensive question which basically says that P's are of 2 type: round represent as capital R and wrinkled represent as small r. In this case, 3 genotypes are possible. Capital R, which have round shape. Capital or small r will also have round shape. Small r, it will have wrinkled shape. And the probability of offspring to be capital R, capital or small r, is given in the table. Like if capital R combine with capital R, then they will always produce capital R offspring, whereas if capital R combine with capital R, then there is 50-50 chance that it will produce capital R offspring or capital R offspring. If capital R combine with small r, then they will produce capital R offspring. An initial matrix representation is also given as P, and the initial distribution of vector is not. Now look at the sixth question. Suppose in an experiment 100 pairs of parent with a genotype combination. Capital R combine with capital R, 100 pair of parent with a genotype combination of capital R combined with capital R, and 200 pairs of parent with a genotype combination capital R combined with small r, are taken to observe the genotype of their offspring. Suppose from crossing of each pair of parent a single of spring is produced. Find the set of the correct option. The first option says that there will be at least 200 of spring with the wrinkled P's. So first, if we try to observe all the genotype combination here, so the first combination is basically 100 pairs of capital R combined with capital R. So in this case, it will produce the 100 capital R and the 100 capital R. Offspring shape is going to be round, so from the first genotype combination, 100 rounds of spring will produce, and similarly from the second genotype combination, again, the 100 round offspring is going to be produced because the capital are combined with the capital R and small r, which have 50-50 chance of capital R or capital or small r, but both have round shape. So from here also 100 pair of round shape offspring will produce, and from the last genotype combination, again, 200 round offspring is going to produce. So the first option is actually wrong, as there is no of spring with a wrinkled piece. The second option says that there will be no offspring with the wrinkled piece, and it is true. The third option says that there will be no offspring with the round P's. This one is false. The fourth option says that all the offspring will have round shape. This one is also true. The fifth option says that all the offspring have wrinkled P's. This one is false. The next option says that there will be at least 100 offspring with the combination of genotype capital R. So yes, from the first genotype combination, there are at least 100 offspring is going to produce in the genotype combination of capital R. And the last option says that there will be at least 200 offspring with the combination of genotype capital R small r. So yes, this option is also true because at least 200 offspring are coming from that third genotype combination capital R and small r, and there are the few more offspring will come from capital R and small r combination from the second genotype combination. So this option is also correct. Now let us look at the question number 7, which says that suppose x not equals 1/3, 1/3, 1/3, find out the correct set of options. So here in this question, first we need to find x1 and x2 also. So in the comprehension, there is a statement given for x1 and x2, which is basically this one, which says that xn minus 1 into p is equal to xn. So by using this equation, we will find x1 and x naught. Okay. So the x naught is already given, which is 1/3, 1/3, 1/3. Let's now first find x1. So to find x1, what we have to do is basically we have to do matrix multiplication of x naught and p. So we are already provided with the p in the question, which is here as 1 0 0 1 half 1 half 0 1 0. So after multiplying x naught with p, the result is going to be 1 half 1 half and 0. And similarly, if we find x2 by multiplying x1 with p, then the value of x2 is going to be 3/4, 1/4, and 0. Now we have all the three values of x naught, x1, and x2. Now we will check the dependency between x naught and x1 first. So if x naught and x1 are dependent of each other, then they must be scalar multiple of each other, means that a times x naught should be equal to x1. So if we do a times 1/3, 1/3, 1/3 is equal to 1 half, 1 half, and 0. Then from the very last term, we can find that /3 equals 0, which basically says that it is equal to 0 now. If we look at the first term, which is basically /3 equals 1 half. And if we solve this, then we're going to get a is equal to 3 halves, since we get contradictory values of a from a same equation. Hence, they're not dependent, they're independent, means that x naught and x1 are independent values. So option 1 is false, and option 2 is correct. Now let's see whether this particular set of vectors of x naught, x1, and x2 are dependent or not. To check the dependency again, we will check the determinant. So we form a matrix using x naught, x1, and x2, where the x naught represent the row 1, x1 represent the row 2, and x2 represent the row 3, and we're expanding along the column 3 as C3 have 2 zeros in it. So we need to do only one calculation after solving its determinant, which is basically 1 by 3 multiply with 1/8 minus 3/8. What we will get is basically 1/12, and we know that if a square matrix has non-zero determinant, then its vector are independent, and x naught, x1, and x2 are independent values. Now if we look at the 8th question, which says that suppose x naught equals a comma b comma 1 minus a minus b, where ab is less than or equal to 0, and a plus b is less than or equal to 1 if the set x naught and x2 is linearly dependent, then find the value of b. Okay, so in this question again, we will find x1 and x2 as in the same approach that we just did in the previous question. So the actual x1 is going to be a plus b slash 2 comma 1, b slash 2 comma 0, and x2 will be 1 slash 2 plus a slash 2 plus b by 4 comma 1 slash 2 minus a by 2 minus b by 4 comma 0. Now it is given that x naught and x2 are linearly dependent, means that x naught and x2 are scalar multiple of each other. So let's do c times x naught is equal to x2, and the equation form will be something look like this. And this equation c say cb is equal to 0 is obtained from the last term, which is basically multiplying c with this 1 and equating it with 0. So from here we can find that either c or 1, b will be 0, or a plus b equals 1. Now let us assume c as 0. If c is equal to 0, then 1 plus 2, a plus 2 plus b slash 4 is equal to 0, and 1 plus 2, a slash 2, b slash 4 is equal to 0. And if we add the both equation, then what we will get is basically 1 by 4 is equal to 0, which is actually not possible. So from this we can say that c cannot be 0 means that a plus b is going to be 1. So later if we solve for the c by using some equations over there, then the value of c that we're going to get is basically 1. And if we put the value of c is equal to 1 in one of our equation, then the value of b we will get is 0. You can pause the video and see the upper calculation for your sake of clarity if you need. Now let's move at the ninth question, which says that consider the set of real number are along with the operation plus and multiplication defined as follow the addition is defined as x plus y equals xy, and the scalar multiplication is defined as c into x is equal to cx ok. In other words, addition and scalar multiplication are both defined by usual multiplication of real number, because in the addition also we are multiplying the two real numbers, and in the scalar multiplication also we are multiplying the two numbers, and from the option below, choose the set of statement that fail to hold for real number addition and multiplication as defined above. So let's see the first option, which says that existence of additive identity, which means that there exists a x not such that x plus x not is equal to x for all x belong to r. So this existence of additive identity will not hold because x plus y is basically xy as per the question. So if we take x equals 2 and x not equals 0, and if we add them, then the resulting will be actually 0, which is not equal to x. So the first option is correct. The second option says that existence of additive inverse for every x belongs to our dr. Exist x prime belong to r such that x plus x prime is equal to additive identity. And there's a not also which says that this fails to hold if additive identity doesn't exist, since we just find that the additive identity doesn't exist here. So the existence of additive inverse is also questionable or not actually. Questionable, it is actually wrong as the additive inverse will not exist here, so the second option is correct. Third option says that 1 asterisk x equals x, which is actually the same as given scalar multiplication, hence it will hold in this vector set. Hence third option is wrong. Fourth option will also going to hold in this vector set, hence fourth option is also wrong. Now if we look at the fifth option, which says that c times v1 plus v2 is equal to c times v1 plus c times v2, so if we carefully look at this option, then we can figure out that it is actually wrong, as if we solve the left-hand side, then what we will get is basically cv1 v2, whereas if we solve the right-hand side, then what we will get is basically c squared v1 v2, so here left-hand side is actually not equal to right-hand side. So this option is not going to hold in this vector set, as this option is correct. And the last option is also not going to hold in this vector set. And we can solve it by taking example, as suppose v equals c1 is equal to c2 equals 1. And if we solve, then we can see that the left-hand side is going to be 2, and the right-hand side is going to be 1, hence it will not hold, means that this option is also correct. Now let us look at the last question, which is again same as upper few questions, where we have to find the value of c using its dependency by finding its determinant and equating it with 0. Just a change in this question is this we have to find for how many c it will be dependent. So let us expand this matrix along c2, and at the end the equation that we got is c squared plus 2c plus 15 is equal to 0. Let's check its discriminant is given by b squared minus 4ac, which is basically 4 by 1 by 15, which is equal to minus 56. WKT, when discriminant is less than 0, then it does not have any real root. Means that there is no any value of c for which this vector is going to be 0. Okay, so that is it for the graded assignment of week 3 for Maths 2. If you guys learned something with this, then don't forget to show your love in any form. Thank you.